if I talk this loud and nobody else is talking, can everybody hear me?
Yeah, I can hear you.
Okay. This section we're going to start today. Now, I know that there's a piece that we didn't get to over here in the last section. This is going to be part of your homework video tonight. And everything leading up to this part here, this box at the bottom of that page, this is still proficiency type problems. So it's not going to be all 4 types of stuff. You do need to at least watch it for that first part in order to get the proficiency type information. All right, and then standard S1. In this standard, we're going to be moving towards the inverse or opposite function of exponentials. These functions are called logarithms. We usually just shorten it and call them logs. There's simple. But the basic premise of a logarithm is that it is the opposite of an exponential. So everything that's true about an exponential, if you reverse it, then it's true about the logarithm. These functions have properties as well, just like exponentials have properties, like when you multiply 2 things that have the same base, you add the exponents. Well, logarithms have kind of the same thing going on. So we're going to first talk about how they're opposites here, define it, and then actually get to work a little bit with some of the properties. All right, so logarithm functions are opposites of exponentials. So with an exponential, let's talk about exponential growth. How does it grow? Does it grow slowly, quickly, kind of neutral? It grows quickly, right? Like it hits something and then it just starts to explode. So with logarithmic functions, if exponentials grow very quickly and logarithms are opposites, then they grow very slowly. Okay, so we're going to list some of these opposite relationships here because they're going to help us when we graph and when we use logarithms. Logarithms grow very slowly. That's probably the very first thing that you would notice about a graph. Something else that an exponential function has is a asymptote. And is an asymptote, well, we know it's that imaginary line the graph can't cross, but is it horizontal or is it vertical when you draw it in? It's horizontal. So if a log function is the opposite, then its asymptote will be vertical. Okay, so we do have asymptotes still in logarithms, but now our asymptotes will be vertical. With inverse functions, we didn't have to do this for the last standard or for the last unit, but with inverse functions, they are opposites because if you were to plug them into each other, then they cancel everything out except for your x. So we actually use that to our advantage when we solve these later on. But one of the main other ways they're inverses of each other is that they undo each other. So a log will cancel out an exponential. Much like if you were to square a square root, the square cancels out the square root because a square and a square root are opposites. So a log and an exponential will be opposites. This isn't really a way that they are opposite necessarily, but logarithms also have bases. Okay, so like an exponential has a base. If it was a base of 2, that would mean doubling over time. A logarithm will also have a base. All right. Let's look at a definition of a log function. Now, I guarantee that you've not seen a log function yet. So this will be a brand new function. We only really deal with the basics of this function in Algebra 2. It's not scary to work with. It's just written differently than we usually see a function. For example, that is how a log function is written. So you know it's a log function because it uses log to represent logarithm. It has a base, and we call the x the argument. You can't just have log by itself, but it has to be the log of something. Just like you can't just have an exponential with a base of 2 and not have it be raised to a power. So we're going to define those here. B is your base value. X will be called your argument. And the general description of a log is that the value of a logarithm is the answer to an exponential. And let me explain it. If you were given 2 to the x equals 2, hold on. How do I write that? Just give me a second. We'll do it this way. Okay, so if I have 2 to the x equals 6, and I wanted to know what that x was, I might say, well, I know 2 squared is what? 4. And I know 2 cubed is 8. Okay, so 6 is halfway in between 4 and 8, so what would you assume x would be? 2.5. Okay, somebody take a calculator for me, and can you punch out 2 to the 2.5? Anybody with a calculator? And every table has calculators, so you should be able to. What is it? 5.65. So is that quite 6? Close. It's close. Can you try maybe other decimals and see how close you can get to 6? Yeah. So take 2 and raise it to powers and see if you can get close to a 6 value.
6. If you have 2.6, you get 6.06.
So if you have 2.6, you get 6.06, but that's still not quite close enough to 6. Try to get really, really close. You can use more than one decimal, too. Try 2.55 or 2.555.
5.8, 2.55.
What do you have?
5.85. 6.342784.
Is what? Oh, almost.
No, I'm 0.597.
5.97? Yes, sir.
Ooh.
Give you guys another 30 seconds or so to get as quick or as close as possible to 2.02. 2.02, that's probably the closest we've gotten so far.
No.
6.02.
2.585.
2.585, and what'd you get for that?
It was like 6.0214.
Okay. I'm going to stop you there because that's probably the closest, because the actual answer is 2.584962501, and then it keeps going on. So remember. Now, and eventually you'll know how to do this on the calculator, but that would have to be what the power was, that 2.584, it goes on forever and ever. That would have to be the power that x would have to be in order to get a value of 6. So like if I took 2 and raised it to that entry, oops, I get the value of 6. Now, to get the value of that type of answer when it's not a nice, that's a nice square, a nice cubic. If you didn't have a table of all these different decimals, it's going to be difficult to find that. You just have to keep testing numbers and keep going out decimals until you get to the value 6, which would take you forever. So they use inverse functions to find that. So to actually find that, they wrote it as a logarithm. logarithm, the value is the value of that exponent, or it's the answer to that exponential. And then this is what I punched into the calculator. That's the function I punched in, and then that got me the answer that I needed to solve that exponential. So logarithms were not invented necessarily, but they were, they were made or formed or just a different set of functions in order to answer the types of questions that were unanswerable by just logic with exponentials. Okay, I think that kind of covered that part there. All right, we will get more into how logs are written and used and solved and all of that, but today all you need to know is that they are the inverse or the opposite of an exponential, and then we're going to cover some of the properties and practice those properties right now. So if you would flip to the other side. Thankfully, logarithms don't have 6 or 7 properties like exponentials do. They have 3. And these properties pop up in Algebra 2. If you take Algebra 3, they'll pop up there, and then they pop up again in Calculus, so they don't necessarily go away. We have a product property. Okay, this would be like in the argument of a log function. So it's log base 2 of whatever. This whatever, if you have 2 things that are being multiplied, this property allows you to break it apart into 2 different terms. So it says, okay, if I have u times v, I can break it apart into 2 logs, separate out my argument into 2 different logs by adding. The quotient property is basically the same thing, except instead of adding, what do you think is there? Well, it's being divided. So if it's being multiplied and I break it apart by addition, good. Then when you're dividing, when you break it apart, it is subtraction. Much like if you're dividing with exponentials, you subtract the exponents, and if you're multiplying exponentials, you add the exponents. Power property. This is if you have an exponent on the argument, so maybe this is like 2 to the 3rd power or something. If there is an exponent in the argument, you can bring it, like you can move it to the front. And just rewrite your term. Now, the reason we work with these properties will make a little bit more sense as we get into the next standards coming up. But today we just need to get good at working with these 3 properties and doing what we call expansion of expressions and condensing. Because these properties work both ways. So you can expand by breaking it apart, and then you can also condense by putting it all into one. So they go both. With example 1, make an A and a B. And I'm going to walk you through several of these. Let's start with the expansion. So maybe write expanding next to the example so you kind of know which ones we're focusing on. And when you're expanding, there's a little, well, it's not really an acronym because it kind of stands for something, but I use these 3 letters to remind myself what order to go in. So the first thing when we look at the problem I'm going to write down, you need to look and see if the argument is being divided. If it's being divided, that's the first thing you break up. Then you look at it again and see if anything's being multiplied in the argument. If something's being multiplied, then you break those up. And the last thing that you break up is a power. And when I say break up, I'm talking about like making it 2 different functions instead of just 1. Okay, so we're going to write log base 3, and that base is like subscript, so it's written a little bit lower. And then in the argument, I'm going to have 3x squared y over z cubed. Okay. And then we're going to go step by step. Now, if you don't go step by step, it's going to seem overwhelming, but that's why I give you these 3 letters to kind of keep us on track. Okay, so if you first look at the argument, is there division going on? Yes. So that would be the first thing that we need to break up. then when we break up division, that's following that second property here. So we're going to break it up into 2 logs with a subtraction sign in between. So I should have log base 3 of the top minus log base 3 of the bottom. Okay, so you break up the division using the quotient property. Then you reevaluate it and look at multiplication. If we look at these 2 arguments of both these functions, is there multiplication going on in one or both of them?
Yeah.
In which one?
The
Front one. So I have actually 3 being multiplied by x squared, which is being multiplied by y. So there's actually 3 different things being multiplied, which means I have to break up all 3 things. So this is going to become 3 different logarithms. Log base 3 of 3. And then what goes in between? A plus, because when you're breaking up multiplication, you have a positive or addition sign between. So log base 3 of 3 plus log base 3 of x squared plus log base 3 of y minus log base 3 of z cubed. Okay, so you break up the multiplication. And the last step is to look for powers. How many powers or exponents do I have in my argument? I have 2, right? This one is x squared, and then this z cubed. The last step, or the last part of my answer, should be to take those and move them out front. So we have log base 3 of 3 plus 2 log base 3 of x plus log base 3 of y minus 3 log base 3 of z. Again, today's goal is just to work with these 3 properties. So that's all we're doing, is just getting comfortable with them and going both directions. So expanding and condensing. Okay, let's try another one. Go log base 5 of 2x cubed over y squared z. I'll try this. Okay, again, follow the little steps here. So first step would be to look for division. When you break up division, which I am dividing here in this argument, I have to include what in between? Subtraction. So your first step should be writing down log base 5 of 2x cubed minus log base 5 of y squared z. Okay. And then, Emily, do I have any multiplication going on?
Yeah.
In how many of the arguments? Both of them. Okay. And when I break it up, Devin, what do I need to include when I break the multiplication up into 2? The adding. Good. So this one's going to break up into log base 5 of 2 plus log base 5 of x cubed minus log base 5 of y squared, because this one will break up as well, plus log base 5 of z. Now, I'm going to group those last 2. Can someone tell me why I grouped those last 2 together? Because what's in front of this logarithm here? A minus, which means I have to subtract both of these. So because you split it up, I do have to just show that you're subtracting both of these because they were both part of the same logarithm here. And then your last step would be to move this 3 out front and this 2 out front, because those are my only powers in my arguments. It's just rewriting at that point. And that would be it. That one. I think what we're going to do is, instead of going to the condensing, I'll just give you a forewarning. Your homework video for tonight will be doing example 2 with u, which is going the other direction. So taking something that's already broken apart like this and working it back to one expression. And then the part that we missed in the last one. So tonight's video will be important to do because keep in mind we're trying to finish these notes this week so that next week we can review and pass on Thursday. If you have anything to worry about, we're just going to wait. Grab a whiteboard and marker and rag. I do want to see maybe if you've picked up what you need to for those problems. And I want you to expand this. Okay. Try to expand that. If you can't find a marker quickly, then do it on a piece of paper and show it to me. Because you only have maybe 3 minutes left, so I do want to see one of these from anybody. Again, if you can't find a marker quickly, just do